what I want to start with is just some reflections on what you wrote about with respect to that article. Had you read the article, I asked you to do 3 things with that article, and then I asked you to respond to 3 of your classmates based on that article. And there's some things that came out I just want to touch on and maybe ask a question. We'll have a little bit of dialogue here in class on it as well. But I didn't write them in here. I just have them on here, so I'll talk, we'll write as we go along. Probably the number one response that a lot of people said is a study based on prayer is complicated. And that is an understatement, but I'm going to even parse that back a little bit and say to do a really well-designed study on anything is complicated because it's how do you control for randomization, replication, control, how do you control for everything? And the answer is you can't. So you have to try to mitigate and eliminate as much as you can in your design, and then what we end up sometimes trying to argue around, which actually the author of the article did, which I was disappointed that they said it, but their argument really is getting to deal with this idea of what's called sampling. Come on, stop moving. Sampling error. When I say sampling error, do not think he's talking about something that's wrong. Sampling error is just normal error that happens. So if I have 500 patients here and 500 patients there, and I can control for all things except for, one got prayer, the other one didn't. So then within that, the author said, well, but we don't know who may have been praying for those that were in the non-praying group, which is true. And we don't know if those that were in the praying group were getting prayer from other people as well, which is also true. And there's honestly nothing wrong with that. That's very normal in any type of an experiment that you're going to do, especially like this, where it's dealing with actual people doing actual things where you can't control for all those external variables like you can if you're studying rats in a lab. But that's called sampling error. It's just normal, expected, and okay error. So while, yes, the author of the article and whoever he was talking to made comments about, well, we don't know all these other things that are going on, they're just talking about and highlighting a fact that that's called sampling error, and that's not a problem. All right, so the article, that's one of the things I don't like about the article, but I don't pick articles just because they're this is the best one and talks about everything that needs to. It's always good, I find, to get reactions, even if it's in educational literature, because they're not always able to, everybody has an agenda, all right? So the author of this article had an agenda, and it comes out as they write. But I just want to go with that as a starting point, but then more to get you thinking here, and this is an actual, honest, I want to hear your responses. Why do a study on prayer? To the question of, so aside from, and you can probably figure out where I stand on this. I would hope that many of your professors would be the same way, in that why prayer and science, aside from the fact that, like I just said, so much of the natural world and study of it came out of individuals who wanted to learn more about God. Why do you think it either belongs together or does not belong together? And give me a little reason why. Share with the class if you're comfortable. So not everybody likes to be the contrarian who says, yeah, I disagree with that, and I don't think they belong together, or I do believe, or whatever it is. So we do this in as best we can, a respectful way in a conversation in the classroom. But do you think that science and prayer belong together? So with my background in looking at data, I tend to try to look at it in all aspects of my life, within my faith and then outside my faith. And I think back to, I remember my mom saying when she was in high school, once they discovered the atom, they said, we will never discover anything smaller. And then from within that, obviously there are subparticles and parts of atoms. And within atoms, there are the elements inside of atoms that have parts. Then you get all the way down to, I heard someone say quarks. And quark is basically a vibration. And really, so the existence and the sheer magnitude of everything in creation is actually not mass, it's vibration. So to me, that makes sense in terms of like from out of nothing, ex nihilo, out of nothing God created. And really all of every substance is actually nothing when you consider it at the most minute level because it's just a vibration. But that's not for this course. So I agree with what some people said. To think and to ponder on certain things is theology, philosophy, all right? But I think good scientists do the same thing. And in a way of, are they trying to prove or disprove the existence of God? That could be part of it. Or you just have people who are in medicine who say, can there be something else that helps? If you've ever thought about medicine, it's the practice of medicine. They don't say it's the craft, it's not like you've perfected medicine. They are always learning and discovering because there's new things that are, wrong with the world and our bodies and everything else. So they start with certain treatments and then they make adjustments to those treatments based on scientific method, analyzing the data. And by adding in that component of does prayer have an influence, there's actually a lot of studies out there that look at that idea. There was one out of South Korea where it looked at fertility, and they worked with, I can't remember how many, couple hundred infertile women, and then they were split and randomly assigned and how they processed through, and then it was all there, and there was what's called a statistically significant difference, which means you would expect there to be a little bit of a difference, sampling error, right? A little bit of a difference when you do different samples. But what they saw happen was statistically so improbable, it would only happen 0.1% of the time by chance. They said that prayer actually did improve fertility in women with those who were getting prayed for than those who were not. And there was all through doing IVF, in vitro fertilization. And there are other, like I said, that's just one other one. There's many, many other scientific studies that are out there that look at the effects of prayer. Some are inconclusive, some are conclusive, and then some have a lot of variabilities and variables that go into that. I did like what a couple of you mentioned when you were just talking about not putting God to the test. Just my caution always is whether the author uses that or you're using that, being sure that we're using our scripture in context. Again, that's not the scope of this class, but always should be at the forefront of our heads. And then, another comment that was made by several individuals is, hey, this was like, I think, 06, is that right? Was this an 06 study? Yeah. I'm saying, that was so long ago. There are a lot of great studies that have been done over the years. Just because something is old doesn't mean it's outdated. All right, an old study can still be very relevant if it was very conclusive. Usually a study like this one, where then we say, hey, there was a problem with this and a problem with this and a problem with this, inspires someone else to do, well, then I'll do a better one, and then I'll do a better one, and then I'll do a better one. And once you get to points where it's showing very clear conclusions, we assume that then, again, whether this is 20 years ago, 100 years ago, or 2 years ago, the age of a study is not, don't always hinge your argument on that. I mean, maybe it's outdated because technology is now better for something that they're studying in those designed experiments. But just because it's old doesn't make it wrong. And then, yeah, and if a study is inconclusive, like this one was, that doesn't mean that there isn't something there. There are, again, so many discoveries that we have talked about and will through this course of this class, and you'll see in your future, that at one point were inconclusive and then later become conclusive because of either better techniques, better ideas, better approaches, better technology, or it could end up being one of those mysteries that always seems inconclusive, but you don't know unless you try and study. So with that, we're going to be talking about data and comparing data today. Why do we compare to data? How do we compare data? So this is where you're going to start with the people that you're sitting next to. Is when I turn you loose, you're going to turn and talk for just a couple minutes on why we compare data and how do we compare data that you know of so far in your vast repertoire of statistical techniques. Ready? Talk. So bias normally comes out from sampling techniques. So I'm going to use this as pretend that this is a target, right? If that's a target, and I had a bunch of data, and that data was all right here. that data would be called low variability, high bias, because it's biased towards hitting this location. If I had data that was like this, that would be lower variability and no bias, because it's hitting what I expect it to hit. But bias can then be determined by, well, who determined what the target was? If it's an unknown target, then the next time I readjust my target to be centered on this to see if it'll do it again. So bias, what we normally think of as bias when we talk about influence and what might cause, that type of bias comes out when we analyze how they're collecting data, okay? And maybe even how they compare data. This type of bias here is then the data that's collected, and here we're gonna use the word bias slightly differently. So that's the challenge, again, with the English language as well as statistics, is we'll use same words and talking about two different things. You have to be really clear when we're doing it and are explaining it, which type we're talking about. Yeah, what do you think? So the question was, couldn't this data here have been from bad technique? And the answer is possibly. All right, if we assume good technique and it's not based on bias like confirmation bias, we're not getting, it's not all the other types of biases we've talked about. Voluntary response bias or something like that. If it's a good process in the how, and we can still get data like this. So if it is bad technique, then both the how will be biased and the results will be biased. In that way, we're actually talking about them two separate types of bias, but we're talking about them in the same argument, which then makes it really careful that we're using our words diligently and precisely in describing what's happening. Yeah. So, low variability, high bias. Less variability, less bias, or no bias, potentially, since it's centered around the bullseye, if it were. All right. But why compare data? Yes. So looking for trends in data, looking if there's some type of a relationship going on either between two data sets or two types of data that we're comparing. Anybody else about why we compare data? Yes?
Figure out why something happens instead of something else.
It could be to look, is there something else going on? Is there some way I could show that this, again, looking for relationship. Like, why is this data going on this way? And usually that's going to come out afterwards. So as a statistician, which you all now are because you're in this class, anytime you're coming up and looking at what's going to happen, you're going to go out and you're going to collect data. And then you collect data, oftentimes you start looking at that data, and then we analyze the data and we compare the data. And from that, it should make us go, I wonder. And then that is the initial stage of starting up and doing a designed experiment. And then you're going to be looking at that I wonder idea to design an experiment, and then you're going to go out and do more data collection using some type of a process, randomization, replication, and control. So at first, we're looking at just kind of like the interest in numbers. I know you're thinking, really? Interest in numbers? Yes. And what is it saying and comparing and showing? And that's why we do it. And then the how we do it is really the course of this study. All right, so we're going to compare shapes, we're going to compare centers, we're going to compare spreads, we're going to compare outliers. And for those of you that are taking copious notes as well, this is being recorded and it will get posted. So if you want to just sit and listen and take it in, that's a better way to do this. As you're going through a class, the other thing you should be thinking of and writing down in your notes are questions about, well, why is this and how is that? Start to build context. We like to do that in class because in a moment, I'll pause this video and you'll get a chance to ask those questions. But if you're so busy writing down the what, you miss the so what. And then you have no chance of getting to the now what, the 3 levels of cognition. So what is recall, so what is interacting, and then the now what, that's when you're talking about really thinking deeply. I was going to use a really big word, but decided to just go. That's when you get to really thinking deeply and you start to integrate ideas, your past experiences, when you get to the now what. Now what are we going to do with all of this information? So shapes, centers, spreads, and outlines. In shapes, there's a lot of different shapes that we're going to talk about, but there's a few that are just going to be like our standard go-tos. we're going to have, and I'll write down the words here so you can see the words. You can probably think of what they mean. Symmetric. Symmetric means like if I had a little line and I drew it down the middle, it looks roughly symmetric. Okay, don't call it symmetrical. Graphs are symmetric. It could be left or right skewed. And if you watch the past video that I did, skew means essentially that one end is pulled away from symmetry. So if I had a rubber sheet and I had a graph on it and the graph was symmetric, and then I only grabbed one end and only pulled on that one end and stretched out only that one end, I'm skewing the data. All right, and I'll tell you what we're actually skewing in a moment. So left and right skewed, we're going to talk about something that's going to be bell-shaped. If you want to talk real sophisticated, when you get with your math peoples, you'd say it's a Gaussian curve after Gauss, the mathematician, G-A-U-S-S. Gaussian. And then other things that we're going to look at when we look at these two graphs here. So these are the graphs of your heights from the data that we collected. It's the same set of data. It's just these have a narrower bin width than these. So this is the exact same data set, and you can look and say, well, they're similar, but there's definitely some differences, even though it's the exact same set of data. But this one right here is the top, so it's just singular. There's one modal interval. That's that one right there. If I had a graph that had one prominent height here and then like another prominent height here, almost of equal heights, we would say it's bimodal because there's two modes, two things that happen most often. But symmetric, left and right skewed, and bell-shaped. Those are pretty much the three here, but left and right are two different ones that we're going to be talking about when we're talking about comparing data. There are many other shapes that do exist out there, but we're just going to, getting that overview. Centers, we've talked about these already, either going to be the mean or the median. This hopefully will be the last day I talk about mode. It's just not that useful of a thing to talk about, typically speaking. It's probably back when you were in like 4th or 5th grade, the first one you learned because it was the easiest one. Which one happens the most often? You look at them like, oh, this one does. Ta-da, that's the mode. All right. The median is the 50th percentile. The mean is the average. So here's what happens. If I have this particular box plot, I would say that box plot appears symmetric. Not only is it symmetric, it actually appears that every quartile is roughly the same length. All right. I could be symmetric with a very narrow box and really long whiskers as long as it's the same on the left side and the right side. But this one is symmetric all across, like all the quartiles are about the same. All right. So what happens if my right end gets much, much longer? It becomes skewed to the right. What is being skewed to the right? The graph? No. The mean. When a graph is symmetric, the mean and median are about the same. So bell-shaped is symmetric. There's other types of symmetric graphs. This one originally was symmetric. But when it's symmetric, the mean and median are about the same amount. If it gets skewed to the right, that means now I've got some values that are really high. Well, that has an effect on the average. If you have one score it's usually the other way around. When you're doing well in a class and you have one test that just tanked and it drops your average considerably, one score can make a huge difference when talking about means and medians. All right? The median won't change. If all I did was took that highest value and made it up to here, and there were no new data points, the mean will be moved up and the median does not change. All right. So the mean can be influenced by larger values. The median does not. So when we say this is right skewed, it's because the mean will be to the right of the median. It gets skewed. It gets moved up because of the extra large values. If it's skewed to the left, obviously that would mean that the mean would be less than the median. All right, spreads. When doing a box plot, which we've talked a little bit about already, the two types of spreads we're going to use when doing a box plot, we're going to have the range and the interquartile range, or the IQR. So the distance from the first quartile to the third quartile is my IQR, interquartile range. That tells me my middle 50%, the spread of the middle 50% is that number. That's the interquartile range. And then the overall range is maximum minus minimum. And as we did just recently, the other type of spread that we're going to talk about on one of the future slides here is the standard deviation. The standard deviation is going to be the words that you're going to hear talked about a lot in statistics. Probably if you take some more of your higher level psychology classes, when you're doing pretty much anything that revolves around any type of a study that's done, which is going to be almost every subject matter, which is why if anybody here decides to ever go on and work towards a master's degree, almost all of them are going to require a statistical methods class as part of that, which is deeper than what we're going to get into in this class, because it's so important to understand what they mean. So you'll get grilled on and drilled on the standard deviation from me because of that reason. Standard deviation means it's the average distance of any data point from the mean. So if you have to memorize that, then memorize it, but that's what it means. So if I have all the heights of all the students in this classroom, and I pulled out one of you and found out what your height was, the question would be, how far would I expect that person to be away from the average height? The standard deviation is that number. The smaller the standard deviation means the more condensed the data is. But then it also depends on context too. All right? But standard deviation takes into account the values of every data point in the data set. So do we get rid of outliers? It's going to be very hard to convince someone to take out an outlier because it's actual data that we collected. So if it's actual data that we collected, in order to remove an outlier, we would have to have some very convincing evidence about why that data point should be removed. Like clerical mistake. We clearly understand there is no way someone had 900 contacts to their cell phone list. I would venture it's the other way around. Whoever wrote one, I doubt anybody has one contact in their cell phone. All right. Now, I would need, unless I can know for sure, I cannot remove that data point from my data set. But what I will do is say, wow, there appear to be a lot of outliers. I wonder why that is. All right. And then, well, we'll get to that. So outliers, we did it with the box plot where it's 1.5 IQRs above the third quartile, wherever that is. So here's my interquartile range. So if I pretend that's that distance, I take 1.5 that distance and add it to here. That would be about that point. So any data point out here would be considered a potential outlier. 1.5 IQRs below would be down here, and that boundary point, there aren't any below it. And that's how you determine it for that. In other graphs, we're going to use the standard deviation and calculations that we'll get to in another future slide here. But let me hit this one other before I go to the next slide. If I'm talking about the average and the mean, the measure of spread that I always use is the standard deviation. If I'm talking about the median, then the measures of spread I use are the range and the IQR. If I talk about the median and then talk about the standard deviation, I am mixing up two values and ideas that should not be clumped together. If you pay any attention to watching the news, reading newspapers, articles, things like that, they talk about median household income. And you wonder, why do they talk about the median household income and not the mean household income? Well, because the mean is highly influenced by large values. If you have a community and you have one person who just has a lot of money, the average household income will be higher than most people. All right, so the median is a nice number because that means that's 50%. The median household income of a region tells you that 50% of the people in that region earn less than that. 50% of the people in the region earn more than that. All right, but if they then talk about the median household income and then they start talking about the standard deviation, that means they did not take my class and pass it because I will not let you do that. Can't do that. They cannot be done together. So the mean goes with the standard deviation. And if you remember from the calculations from before, to calculate the standard deviation, we use the mean. That's how it's calculated. Now, are there measures of skewness for the median? Yes, but we probably won't get to that in here. Only because it's inconsequential for the work we're going to do in here. If you want to look it up on your own, you're welcome to do that. It's actually just it's sometimes called kurtosis, but it's the skew factor for the median. I want to go back here for a second. So here's a data set. Don't have to look at that too much, but this is typhoons from 1997 to 2010. The dashed line, Western Pacific and Eastern Pacific typhoons. The dashed line is the actual data numbers. This line here is what's called the lagging average. So they take the past 3 numbers and then add them up and average. So this one plus the last 3, and then those 4 average to this point. This point is that data point plus the last 3 from that, average out to here. And what it starts to tell you is a better sense, because every year you're going to have ups and downs in data. But if you do what's called a lagging average, you can then see more of like a trend of what's going on. So while you may not have noticed, I think you probably could looking at this dashed line, it's going down, but here you can clearly see it's going down. This dashed line, it's harder to notice, but it does have a very slight increase or uptick in number of typhoons on a 4-year moving average or overall over the past, well, in this case, since 1997 to 2000. So while there might be there's always going to be the variability year in and year out, the overall trends you can't see until you do some other aspects to it. But it gets back to, why do we compare data? We compare data looking for trends, things going on, and then from that make hypothesis, well, why are typhoons going up in the east and down in the west? And what else can we be looking at for what's happening and why that might be happening? And then if you're going to become a meteorologist, what that is going to mean for your career and the implications for the residents who live near there. And again, data is everywhere. Relative positioning and percentile. All right, relative positioning and percentile rank. So correct me if I'm wrong, you don't have to take the SAT anymore, do you? To go to college? Nope. Yeah, well, he says you're welcome. It depends on the school. It used to be always the best way to describe what's going on here, because you're going to do all of your standardized testing. Maybe back in elementary school, you sat down, you took either the Iowa skills-based nationalized norm test, you took the California achievement test, you took Terra Nova, there's so many different testing agencies that are out there. And then, of course, you have the College Board who owns the SAT suite, so PSAT and the SAT. But what happens is you take these tests and then you get a little number that says this is your percentile rank, right? So it gives you your percentile rank, and it says something like 68th percentile. And you go, whoa, that doesn't seem great because 68% is a D. That's not what that means. 68th percentile means that 68% of all the other people who took the test scored lower than you. All right, so the 68th percentile means 68% of those who took the test or did whatever are below you. If I looked at the heights, I'd looked at 5 feet 10, which was 70 inches when I looked at that spreadsheet that I've sent out to all of you. And then I sorted them all from lowest to highest. I said, the 70th, there were actually 3 people who said they were 5'10". There were 3 individuals. And the lowest one was the 37th person. So in listed order, if I listed all the people that took this survey by height and counted from the bottom up, the 37th person was 5 feet 10 inches. And then to calculate percentile rank, you would take, 37 out of 71. And that would tell you your percentile rank, which is going to be just a little bit over 50, right? Because 35, 35 is half of 70. So 35 and a half is half of 71. So the 37th person is a little bit taller than that. So 5 feet 10 is just a little bit over the 50th percentile. And so then you're looking at that and you can say, that doesn't seem right. It seems like 5'10". Isn't 5'10" about average height for U.S. Americans? I don't know. Typically for men, it's right about 5'11", I think is what average height is. Again, these are numbers that I don't pay a super close attention to. Again, average height, meaning you're going to have some people that are really tall that skew it up and others that are short that skew it down, but it's typically in that region. But when you're talking about your percentile rank is your relative positioning. Relative positioning and percentile rank, I will use almost synonymous. All right? Relative means out of how many. Anytime you see relative this or relative that, we're talking about what it is as a percent of the whole. Relative positioning. All right? So 68th percentile would mean 68% of all those who took this were at or below me. The only thing you're not going to see, you cannot be in the 100th percentile. Because everybody cannot be lower than you because you're one of them. Because that would make you lower than yourself. You're like, but what if my positioning is the 71st position? Then you were at the top, and you would technically, by using this little definition here, 71 out of 71, you're the 100th. But that doesn't mean everybody is shorter than you because you're also you. That's the only little weird caveat to this is when you're doing percentile rank, you don't get ever to be in the 100th percentile. What if I ace the SAT? What does it say? It says you're the 99th percentile. So quick refresher on standard deviation. You do not need to know the formula, but we walked through it. The standard deviation, that's lowercase sigma, is equal to the square root of the sum of capital sigma, each x value minus the mean squared divided by how many data points there were. And the standard deviation is the average distance of every data point from the mean. And the standard deviation, again, is if I take every data point, subtract it from the mean, that's how far it is from the mean, square it, add them all up, divide by n, take the square root. The square root in concept, although mathematically it's incorrect what I'm about to say, the square root and the square are then inverse and canceling each other out. I never use those words actually with real math because that's not really true. But you're finding the average distance of each data point from the mean. If you don't square it, here's what happens. If you don't square up here and you just take the difference and you add them all up, it gets to be 0. Because the average is all the numbers added up divided by how many there are. If you take how far away each data point is from that, some are above and some are below, but how far they all are above and how far they all are below is the exact same number. That's what makes it the average. So the difference of every data point from the mean, if you add just those up, you actually get 0. So standard deviation is going to be used in lots of ways. Chebyshev's is the least fun and least influential idea, but it's an idea that's out there. This is if you have no idea about anything about a data set, nothing, you don't know what its shape is, you have no clue about anything else. K is the number of standard deviations. And here's what it says. If I want to know how much data is 2 standard deviations away from the mean, I would take and go, all right, 1 minus 1 over 2 squared. How much data is 2 standard deviations away from the mean? This would be 1 minus 1/4, which is 0.75, which is 75%. So my response would be, there is at least 75% of the data within 2 standard deviations of the mean. And when I say within 2 standard deviations of the mean, if this is my mean, if I would take the mean plus 2 sigma, I'd get some number up here. And if I did mu minus 2 sigma, I get some number down here. And I'd say if I looked at all the data points in this interval, I would expect to see at least 75%, which is not much. But this would be if I have no idea about anything about the distribution and shape. Just understanding that this principle exists is about all you're going to need to know for me. Don't be like, I got to memorize that formula. You don't. That's also a good point. Most formulas I don't make you memorize anyways. That's what the internet's for. So I'll give you a formula sheet typically that shows all the formulas. So this would be on there. This would be on there. It might not tell you what it is, That would be up to you to remember that, oh, that's Chebyshev's, got it. All right. This is more important, which is why it has a much better name, the empirical rule. All right? The empirical rule says this. With data that follows a Gaussian curve, aka a normal curve. A normal curve has a mound in the middle. Sometimes it's called bell-shaped because it kind of looks like a bell. All right? Mounded in the middle, roughly symmetric. This trails down and becomes asymptotic to the graph at the bottom. Asymptotic, asymptote. It doesn't ever actually touch there. It just keeps going out infinitely closer to the horizontal axis, and then down here. In this, the middle, which that should have been there we go. The middle is the mean. And in a bell-shaped curve, I would expect 1, 2, 3. So this is going to be that point right up there is going to be mu plus 3 sigma. 1, 2, 3. That's mu minus 3 sigma. And because I counted 1, 2, and 3, you're probably guessing yes. This is mu plus a sigma. This one's mu plus 2 sigma. And then vice versa. On the other end, it's mu minus a sigma, mu minus 2 sigma. So the mean, if I were to go 1 sigma up and 1 sigma down, how much data is in this zone? 68%. So 68% with a bell-shaped curve. I'm going to expect there to be approximately 68% of the data within 1 standard deviation of the mean. Within 2 standard deviations of the mean, so if I look at here to here, and then I think about this, obviously it's going to be more than 68 because I've now included all the 68 in it, but in red there, within 2 standard deviations, I expect there to be 95% of the data when something follows a bell-shaped curve. And then within 3 standard deviations, depending on which stats books you look at, 99.7%. So with a bell-shaped curve, I would expect that within 3 standard deviations of the mean, 99.7% of the data will be within 3 standard deviations of the mean. If I'm beyond 3 standard deviations, that would be out here in yellow, or out here in yellow, which together is 0.3%. Very, very unlikely to be in that zone. Those would be probable outliers. Remember we did outliers with the IQR or the box and whisker plot? Here, this is how we do it with a Gaussian curve, or a normal curve. To be an outlier, if you're beyond 3 standard deviations above the mean or below the mean in a normal curve, you occur 0.3% of the time, which is very, very, very unusual. Which makes you a probable outlier. We will very rarely say this is an outlier. We will say it's probably an outlier. Why? Because statistics is the land of probability and uncertainty, and we say almost everything with a level of uncertainty. Notice the hypocrisy in that statement. Everything with uncertainty. But that's what's going on. To determine is it actually an outlier becomes much more complicated and for study in a further class. All right, so that's the empirical rule. On Canvas, I already talked at the beginning of class that I made the mistake. I didn't publish the one thing, so now that it's published, you can go in and submit that box plot you were supposed to have done. Someone asked me, the box plot you can download the box plot as a JPEG, correct? And I said, submit a PDF. So take the JPEG, insert it into a document, type your responses, so that you have then a document that has your box plot in it and your words in it typed out. Then you can save that or export it as a PDF. That's what I want you to send to me. For those of you that use iPhones, which seems to be a lot, when you take pictures of things as well, and this is like more advice for me and all future professors, yes, I can open them because I run on a Mac, so it comes in as .heic. If you did not know, it does not come out as a JPEG. That means you probably have your phone setting to live. If you take it off of live, it'll save it as a JPEG. So if you send something like that to a professor that doesn't use a Mac, they're going to be like, I can't open your document. I can't open your image. If they're asking you to upload images, So be very aware of what technology you're using to make sure you're actually going to upload something in a format that the professor can read. Like I said, for me it doesn't matter because my computer will pull up all of it, whether it's a JPEG, a PNG, a .heic. .heic, again, that's when you're doing live photos on an iPhone. So be careful if you're an iPhone user that you save things appropriately if you're taking pictures and uploading it anyways. So that's what's going on there. The quiz, this is what this says. There is I say quiz in quotes, it's not an actual quiz. You get to do it as many times as you want, and you should until you get a good score, or your best score, which should be 100%. But this gets you at an idea of how I ask questions for tests. So as you are working through the chapter 1 and chapter 2, and now soon to be on Wednesday, chapter 3 problems that I say to do out of the book, online book, that you're doing, you're checking your own work so that you know that you understand it. Then you'll get a sense for the type of questions I'm asking when I give tests and quizzes based on what you see in this quote quiz. And I think I have it due like it's a February date. I don't remember what it is. If you are getting to the place where you're working on all these problems and you have questions and you can't get answers from your fellow classmates, or they don't have someone at the Student Resource Center who can answer your questions, email me, set up a time. I'm here before, like today I was here at 8, sitting in the coffee shop working all morning. I can come in and be on campus because I don't have office hours, remember? I don't have an office phone number because I'm an adjunct. So if you need to reach me and we need to sit down and do that, we can.